Okay, I think we are ready to start. So thank you everyone for joining the FKI Machine Learning Coffee Seminar. And today we have Professor Jörg Tiedemann from the University of Helsinki talking about a new toolkit for multilingual NLP. Thanks so much for coming, and please go ahead.
Yeah, thanks a lot for the introduction, and thanks for coming as well, now when it's cold and the winter's here. So I will be talking about this cute little thing here, the MAMMOTH, but I come to this a bit later. So in general, I will talk about language technology. So I'm leading the language technology group at the Faculty of Arts, actually. So we are in the Department of Digital Humanities, and we are sitting in the city center campus. But we are working on all kinds of natural language processing, but one of the most important focus areas that we're looking at is multilingual natural language processing, and especially also machine translation, so very much applied technology. So just for getting motivated, why this could be interesting, what I would like to talk about in modularization. So of course, no one can escape nowadays those large language models that have been really taking the scene, not only in language technology, but all over in any kind of machine learning and artificial intelligence research. And we have seen a very dramatic rise in size and applications that come out of those kind of big language models. And we can really see that from the beginning, when the transformers were introduced here at that point, actually for machine translation in the beginning, there was a really rapid development where transformers became the all-around tool that everyone is using for everything. So nowadays, NLP basically consists of transformers applied to different kinds of applications. And then there's different kinds of milestones. So first of all, there were some kind of pre-trained models coming out. So suddenly people realized that we can pre-train those models and use them then in some kind of transfer learning for different tasks. And then more and more data was used for training those models. The size went up, and there's a lot of scaling happened in terms of size and capabilities of those models. And we all know that now there's a big hype around those big models, commercial models like GPT-4, which has become gigantic if compared to the beginning. So if you look now at those sizes here, so that those models have 1.8 trillion free parameters that have to be tuned. This is gigantic, of course, if you look at a learning problem here. But also they become really gigantic in running. So there's a lot of costs, not only for training, but especially for inference. So running those is one of the biggest issues. So those models are kind of close, so we don't know much about them, but there are some details that we know. So there's trillions of tokens that they have been trained on. They have massive amounts of different layers to have all those parameters in the network in one monolithic kind of network. So this is a trend that we have seen, but of course we have a lot of challenges. And here's a challenge slide. So one of the things, of course, related to the scalability. So now we have scaled already the models to some really bigger sizes, but we're hitting now actually also some kind of ceilings for how much we can increase those sizes of dense transformers, meaning that all the information is distributed over all parameters. So with current hardware and the budgets that we have, we cannot really scale up those models anymore. They need to be distributed in one way or another. So the GPT-4, for example, is a mixture of experts, so that there will be some kind of modularization inside already. Then another challenge is also this multilinguality, and this is of course something that we are very much interested in. We know that there's a lot of multilingual models around already, and those large language models typically support quite a few languages already. But if we assume that we have a few thousand languages in the world, we have still a long way to go to really increase the coverage of languages inside of those models. And as they become essential for all kinds of tasks, this is really one big issue. And then one other thing is, of course, also how can we, if we now have those huge costs of training them, how can we do efficient training, that we distribute training on large compute clusters, and how can we continue learning? Cannot always start from scratch anymore, so there will be some continued learning which needs to happen to make this actually working. So this also relates to reusability. So we want, and of course that's one of the great things of those models, is they can be reused for many things. So reusability is already there. but there's challenges on how can we really efficiently adapt things to different tasks, how can we make those fine-tunings, how can we recombine different components and different kinds of models, as we have now plenty of alternatives that have been developed. And then the last thing here, this inference efficiency, I think that becomes really a crucial problem, as we have those huge models that cost a lot of money for just running them. This will not work out in the long run, as this is just an energy consumption that is not really justifiable. So we need to talk about this inference efficiency here. And then a lot of other questions that we will not go into this talk too much. Of course, there's also a problem of having those models that we don't really know how they function, what kind of how they function internally, and how we can explain the outputs that they do that they produce. So in what way do we have interpretability and explainability from those models, and do we know how they work transparently if we don't even know for those closed models like GPT-4 what they are trained on, and how do they align with human values? But I will not talk much about those things, so that's a completely different topic. So, but what I want to stress mostly in this talk is modularity. Modularity as a way of dividing things into different components so that you can more efficiently use those components independently. So, of course, here the idea is that we have a bit more efficient use of those systems in inference at inference time. So there's different ways of doing or producing some kind of modularity. If you think that, okay, we pre-train some monolithic, big, gigantic large language model, then a lot of work has been done into adapting them with certain modules that you can just plug into the network, and they adapt to different tasks. You probably know quite a lot about that already. So there's adapters and different ways of inserting them and fine-tuning them for certain tasks. And then you can even nicely combine them so that you have adapters that, for example, adapt to certain languages. You have adapters that adapt to certain tasks, and then you can even combine them, saying that you get that task for a different language. So this is kind of nice. A lot of research going on into that direction. What is still problematic here, so if we assume that we still have this gigantic big language model, pre-trained model, then with the adapters, we basically add yet more parameters to add on this kind of big model. So at inference time, we still have to load and run the entire big model. So that's why there's also other ideas of doing some more network sparsity in dividing models into different components. So let's say modularity, as we see it, is basically some kind of network sparsity where you can say that things are activated in different ways. So depending on the task that you're having, you're activating different sub-networks, for example. So there's approaches of sub-network selection, and then fine-tuning those parts for adjusting them to different tasks. And then this could lead to a separation of different parts of a network. Then we have all the work, a mixture of experts, which then kind of train some gating function that distributes the efforts or the expertise of different subparts of the network. And another way would be to more a priori designing some kind of modularity, so that we would already define that certain components have different tasks. And this is basically what we want to look at. So the MAMMOTH toolkit that we're developing is basically in this paradigm where we predefine some kind of modularity. It's just kind of building component blocks that can be put together in a bigger network, and then once we have trained them, we could more easily plug and play with those different kinds of modules. So we could call this some kind of static routing. Depending on the task, you take different components depending on what you want to achieve. Anyway, so if you have any questions, you can always ask also in between. But so that's basically the outline, what I want to look at, and then just more specifically going into what we developed here. So as I said, I'm especially interested in multilingual natural language processing, and there, of course, the difficulty is that we have to support all kinds of languages. So now this is, of course, just simply illustrating that we want to have some kind of new language model that can read and write different languages. So for Spanish and German, French, and this is Albanian, I think, Finnish, all kinds of languages should be able to read and to write, and then doing kinds of different, adjust to different kinds of tasks. Now, if you see that picture would symbolize that, okay, we have just one big shared model that shares all parameters. Modularity basically in this setup could be seen as just shrinking the shared part. So that kind of circle of whatever is shared across languages could be made smaller or bigger, and then we can define the reading and writing tasks for different languages as different tasks that can be more depending on the language. So some kind of specific modules. So that's the motivation in the multilingual setup, that we have actually quite a clear division of something that could be into more language-specific components and some shared parts. So, this was very simplistic as an illustration, but there's many open questions here, and that's what has kept us busy for the past years. That we want to see in what way can we balance between this parameter sharing and building components that are language dependent somehow. So how can we make sure that we still have effective transfer learning, so that we can have some effect of learning in this continuum of languages, so that they help each other. So we need some kind of sharing of parameters to make that possible. But on the other hand, we also want to have components that we can really separate from each other, so that we, in the end, at inference time, we can really take large portions of the network away and keep them independently from the others. So there's really an open question on what is the perfect way of sharing, what is the perfect way of doing something more independent. And once we have some kind of architectural ideas what to test, then of course also the question is, if we have very complex ways of modularizing things, how can we still train those networks in a very efficient way? So we distribute all those components to different nodes, compute nodes, for example, and we can train efficiently all those different parameters that are distributed all over the compute cluster. So I come back to this later on also. So this can become quite complex as we want to have very kind of diverse types of architectures that we want to support here. So it's not just splitting, for example, a certain big network into different layers and then distributing them, or just having copies of the entire model everywhere. Distribution here becomes much more complex as you want to distribute different kinds of components to different nodes. So that becomes quite a complex structure, and then we have to take care of that we don't lose nodes that are just waiting for others. So we need to have a good way of distributing the training task. So we want to minimize, of course, this kind of communication overhead, and then also schedule between these different tasks, like different language learning tasks. So then again, I also step a bit further away from just plain pre-training with language models, but we actually look a lot at machine translation. So all of the things that I'm presenting here are related to training for the translation task, which is a natural thing in the cross-lingual setup, but of course could also have other kinds of tasks that we combine in a similar way. So that's the MAMMOTH, that's the gigantic kind of scaling of the emoji. So we came up with this acronym as the massively modular multilingual translation model in Helsinki. I think that's the acronym for this. We forget about this. I think we wanted to have a MAMMOTH. So okay, let's. So as I said, we have been working on this for quite some time, and the problem is that engineering takes really a lot of time to optimize those things. We are working now on a framework that makes this very flexible and dynamic. But we have been studying this kind of modularization for some time, and we started with a model that we call the attention bridge model. This takes the idea to more or less to the extreme, saying that if we see this as a sequence-to-sequence model, so an encoder-decoder model in a normal way, that we would plug them together. But so now we would like to have language-dependent components for each of the languages that we want to support. So we have, let's say, transformer models, transformer encoders for each language separately, so they will have their own kind of parameters, and the decoders would also have just their separate kind of module. So all the decoders are independent for dependent for each language. And then we create some kind of bottleneck in between and say all those encoders, what they produce, their encoding needs to go through that kind of shared, one shared layer of some connecting attention bridge. What this does is basically is like a self-attention that you have in transformers. You would have some kind of inner attention that summarizes the entire sequence into, in this case, into a fixed size representation in the middle. So in this case, we were especially interested in having nice cross-lingual representations that we also wanted to test for other kinds of downstream tasks. So the idea was that if you train this to all those different languages, we would get a nice, almost language agnostic representation that really abstracts to some kind of high semantic meaning representation. And if you have this kind of fixed-sized representation, this nicely fits into any kind of classifier or whatever you want to test the content that has been preserved in this representation. So, but on the other hand, we also have the effect that we have those nice little language-specific models that can be kept quite small, and we have also a very minimal shared layer. So the first test was, does this really work? And I just had one figure here. So this is for the initial kind of experiments where we tested this on a multilingual translation task. And here are some results of just translating image captions in 6 different languages. I don't remember. A number of languages, and then we can plot, for example, what happens if you just train a bilingual model to see what is the performance of just training this architecture, which is the bilingual signal as a normal translation task, fully supervised. The dark blue bars would show the evaluation scores in blur. I don't know if you know blur scores. Is that familiar? Some kind of measure where you measure the translation output to reference translations that humans have performed. So it's a very approximative kind of measure saying that, okay, better scores would be more correlated to human translation, but it only looks at one reference translation most of the time. So it's a bit of an approximation, but gives quite a good approximation. So higher scores are better. So this dark blue would be basically the baseline. And then we can see that if we add all the different languages, one effect that we want to see that also more information can be picked up by having more languages so that the intermediate representation becomes better, more abstract, more kind of rich in terms of meaning preservation. So we can see that in all cases, the multilingual signal increases the performance of those different languages, even though we don't improve or don't increase the size of the training data for that particular language pair. So we get something out of this additional signal, which shows that there's some kind of transfer learning is happening, and that is a good result. And another good outcome of this is that we can also perform zero shot. Maybe we could go back to the picture. If we don't have any training data for Czech to French, but we train all those kind of different other combinations, then the system can still read, check input data, make some kind of representation, and produce, for example, French output with the decoder that has been done for the French output. So that is kind of full shot setting also works quite well, but you see in some cases we have quite a big drop, but you always have some kind of drop. So that's the basically zero shot training where you don't have any explicit examples, so more or less unsupervised. But of course you have the input signal, the input languages are in the training, and also the output languages, but not connected. So this is motivating and shows that this kind of modularized model or system can work in this particular setup. So now we also found out that because of this very small bottleneck in the middle, we don't have a high capacity, so it doesn't really perform as well as a completely shared model. So we can't really get the same performance. So that leads to the question, so how much sharing should we do, and how much should we have things more dependent on the language? And that's another case study where we wanted to look at on a larger scale, what kind of sharing patterns would be most beneficial for setting into some kind of modular architecture. So for that, we set up the system, basically what is now MAMMOTH, where we can define a priori what kind of sharing we want to implement. So that we can freely choose as a hyperparameter that how many of the encoder layers, for example, should be shared across all languages and how many layers should be language specific. So we can just set a number and say, okay, 3 of the transformer layers will be shared, or all of them will be shared, or nothing will be shared. We will have everything just language dependent. And then the question is, how does that affect the task fitness, so the translation performance? Another question that we have is, of course, how does it affect the encoding representations that the encoder produces for all those different kinds of inputs? And then also see whether different sharing patterns also lead to different types of language independence in this kind of shared representation. So now some figures here that might be a bit difficult to decipher. So I just don't give you all the details of the setup here, but just quickly showing you that we have different types of also looking at multilinguality. So we take data from our collection of parallel data sets where we can just vary how many languages we want to include. So we actually went up to 72 languages, but here's only showing up to 36 languages. What happens if we have this model and then vary the number of sharing layers on the encoder side? Those colors also not particularly brilliant, as green and green might be a bit difficult to see here. So this is for the pre-language setting. But what this means is that we have no sharing at all up to sharing all layers in the encoder. And what we can see is that it basically is quite stable here, and we can see that sharing all layers is not always the most, not even for the translation task, the best kind of setup. So some kind of modularization can be even beneficial for the translation task. So it's not necessarily the case that we want to just have a big, gigantic model that shares everything. And we can also see that by having more language independence, we don't really lose a lot for the translation task that we are training. Yes?
So does it matter what languages you choose in this?
Yeah, so
choose something that are very similar, right?
Yeah. You pointed out immediately some big question here. So what we made, of course, design decisions here, and we decided for this for languages that are very different from each other. So maybe that was a bit to our advantage, but we also wanted to see how kind of flexible the system is in picking up information for diverse languages. So most of those I have somewhere slide with all the languages. So I don't know, maybe we can go there. No, maybe I should not do this. But so what we did is we selected the diversity. Diversity was the first goal because we also wanted to see whether diversity pushes for semantic abstraction. That I believe, of course, very strongly that if you have related languages, you would have much more effects of transfer, and then sharing probably becomes much more important. But we should run that as well. I mean, there's so many things to run that it's difficult. Then, of course, we have some related languages also in those sets for 36 languages. So we can have a look at the end, maybe if you have time, what kind of language we chose. Another criterion was that we also wanted to test those semantic content and language independence. And there are certain test sets that we need to use those languages so that we can actually make those tests. So that was also one of the types of criteria. Yeah. So not really, well, some answers at least. So this would be the supervised case, by the way. So another restriction is that we use English-centric data. So all languages are aligned to English. So we only have English to other languages. That's a quite common setup. What is good about that setup is that we can also easily test zero-shot translation, as there's many language pairs that are not represented. We have only from English and to English as a translation direction. And this is the zero-shot setting. And of course, there I can imagine that for zero-shot, we want to have sharing, because otherwise you can't get that kind of jumping from one language to another if you don't have shared components that make it possible to go through this kind of representation. But even there, we can see that, okay, we have an increase when we share more layers. but it's not necessarily the best to share everything. The P-language thing is maybe a bit weird here, so it's an outlier in some way. But you can see that 4 or 5 layers is probably somewhere the optimal here. And then having some kind of independent component is also beneficial, even if you want to do this kind of zero-shot translation. So again, that's kind of a positive outcome of this this study. To make sure that I'm not running too much out of time. So as this kind of preliminary studies, just to motivate, we really want to go forward. Maybe I don't spend too much time on this either. So this is for the language independence, and the interesting things are the dashed lines here, because that's across languages. So you train a classifier on English data for natural language inferences here, some kind of semantic task, reasoning task. And then you test on a different language. So then after training a classifier for English data for NLI, you can use this kind of representation that should be across languages. You can also use that for classifying other languages. And that's what you test here. And you can also see that the same effect that it's increasing if we share a bit more. So it's good to have a bit more, we get more kind of language independence by increasing the amount of sharing parameters, but it also doesn't have to be everything. All this motivating somehow that we can do some kind of modularization. And very quickly also looking at other kinds of benchmarks. So I don't know if you've heard about GLUE and all those kind of NLU tasks, so natural language understanding tasks. They're collections of different types of reasoning tasks over languages. And just for testing, how does that work for English, Arabic, French, and Chinese? Again, with the same setup that we have different ways of sharing the layers. Does that affect the way of how that kind of representation can be used for all those different downstream tasks? But I would like to get also more to the MAMMOTH, so let's don't spend too much on that kind of slightly. How much time do I have actually?
About 20, 15 minutes.
Okay, yeah, that's good. Yeah, so I think what I want to show with this is that, so of course we want to scale this up a bit, so to have more languages, and we want to wanted to know whether this modularization does really work. Is it stable enough to do that in a large scale? So I think that is motivating enough for us, at least, so that we can go ahead with this idea of modularization. So let's try to make this really systematic. And that's where the MAMMOTH came into the picture here. So now, as we know, there's different kinds of setups of different sharing strategies, different kinds of architectures that we would like to test. We want to be as systematic as possible, but also on a large scale. So what we need is a framework where we can set something up that we can run for a long time, just with different kinds of settings, and compare systematically what happens if we have different sharing architectures, different kinds of bridges, for example, and what happens if we also define different ways of combining, for example, languages together. And especially the complicating part is that we want to have this trainable on a distributed setup, so that we have a kind of large supercomputer where we can distribute the training to lots of different nodes. So that is what MAMMOTH tries to do. So it tries to give you all the frameworks that you can define, the sharing architectures that you would like to test with all different kinds of possibilities, and then make it possible to just run large-scale experiments on a cluster with hundreds or thousands of nodes, so that you can distribute the task efficiently across those different nodes. And here, this already shows that we wanted to be as flexible as possible, that we can define lots of different variants of sharing and components that you might want to consider. So I will go into some more details about those little boxes, but you can see here already that we don't want to restrict ourselves only to, let's say, some encoder components for a specific language, but we also want to group them together in language groups, for example, and building some kind of hierarchical structure. And then going through some intermediate representation, for example. And so different types of modularity and doing this efficiently in training. And then, of course, the idea is that we want to also be very practical. So in a sense, this framework should also allow us to train now a big, gigantic model over hundreds of languages. with all those kind of component-wise modules. And then making it possible to really take it apart so that you can use those different kinds of small pieces and put them together at inference time according to your needs. So if you would have a very big model with all kinds of languages supported, then you would, for a specific task like translation from German to French, would only pick those components that you need for this particular inference type. And then, of course, you would not need access to the entire global network. Yeah. So that's the idea that then people could plug and play like with Lego bits, putting them together and use just that part. So quickly summing up what kind of sharing architectures we would like to support here. So one baseline is, of course, sharing everything. So that model has been proposed in 2017. It was basically just a very simple trick. So you have just a big encoder-decoder model where you just have some little thing that you need to add. You need to inform the system to say what kind of output languages has to produce, because otherwise it would not know what things to generate in the decoder, because there's no other way of telling the system. So this is early days prompting, I would say, because this is a kind of a little prompt saying that produce German from this kind of input, and then the system recognizes, okay, this kind of symbolizes that I should now produce German. And this surprisingly works well. At that time, prompting was not invented as a term, but I think this is already the kind of first way of instructing. So that is supported, of course. Then we have partial sharing schemes, and that's related to what I said before. So we can freely choose how many different layers should be language specific, or for example, language group specific, and how do they connect to each other. You can also have universally shared parameters, so that you have lots of different ways of building architectures that have different partially shared components. And then you can go up to what I've also shown already, so that you have basically completely independent modules and you only connect them with some kind of cross-lingual attention together with each other. And that also works, but we would like to know, of course, what is the optimal thing. So this is what we have supported. Then I showed already the bridge architecture. This is exactly the same as before, but you can also implement a bridge in various different ways. So one way was this kind of fixed sized intermediate representation, but we can also have some kind of transformer layer as a bridge in between, or different ways. And I actually need to look up also the differences of those implementations. So there's 5 different types of those intermediate bridges that we can activate in the system. Yeah. Now this is just repeating. Okay, I don't really have to say that, but I come later a bit back to that. This grouping, of course, is also interesting. How do we decide what kind of grouping do we want to have? Do we want to have existing linguistic knowledge of how to group languages together, or some more data-driven way of statistically grouping or clustering languages? This is without any bridge. Okay, so all those kind of things are supported. And then, of course, this comes down to the actual implementations, and that means that we have to write some configuration files to configure all those different modules. And this is just some snippets on how this is defined. So we define different tasks, language pairs, basically a task, and then in this example, those kind of components are dependent on the language. So they don't share anything, which means that now they become dependent on that kind of language data, and we show here somehow what kind of components they are. So they have 6 transformer layers in this example. And then if you have more partial sharing, then for example, we can define different sharing groups here in the encoder side, just for a specific language, or universal for all languages, and then give how many of those layers should be then implemented in the architecture. And here would be completely shared as a setup. So as this becomes a very complex configuration file, one of the tools is also that there's a script that can generate this kind of configuration file. So this is maybe one of the nice things we are trying to develop, to make this very straightforward to implement certain ways of, okay, I want to have this kind of language groups generate the configuration file that we need. So this is our famous config. That does also plenty of other things. Then another important tool is a task allocation tool. And this means that we need to also find a good way of distributing the system or the architecture into different nodes for training purposes. So here this is a highly complex problem. It's not really solvable in general, but this is a tool that optimizes in some way to distribute those different components to different GPUs to make the least overhead of communication that we would expect. So this task allocation tool is quite important to distribute those different language tasks to different nodes, seeing that we have a more or less even good distribution here. And then, of course, while training, as I said, one of the important things is that we want to have distributed training, and that means that we have to implement some algorithm that does the updating of parameter values in the most efficient way, that we don't have a lot of communication. So that certain things are only communicated if needed. So we have language-specific components, and different components create certain kind of gradients, then only on those nodes we will keep information and then broadcast when needed and need to be synchronized. So that becomes, as you can imagine, quite a complex beast. So there's an algorithm that has been implemented to make the least possible overhead for doing the communication between the different components. So you can see that those nodes can be really very different from each other. That makes it a challenging task here. So then just last weeks, we were looking at scalability, and this is still a bit preliminary. So we are really working hard on getting this done for large scale experiments. And scalability is actually very promising here in this picture, especially. So here is testing for up to 5 nodes. So we have 4 GPUs per node, and then trying to see whether we have an increase in throughput in terms of tokens per second when we train with increasing numbers of increasing tasks, basically. So we now increase the task in a set where we have a constant number of tasks per GPU. So we define 3 tasks per GPU. And see whether we can get an increase of a linear kind of increase of tokens that we can run through the system. And this is tested on Bukti and Bhakti, so the supercomputer CSC on NVIDIA GPUs, and it's almost too good to be true. So the blue line is the baseline, meaning that we actually somehow exceed the baseline, which should not be possible. But then you have to consider that this is natural language data where we do all kinds of tricks like padding, so things are different length. So it can happen that you actually become more than linear in scaling up here, as you might have a bit of a suboptimal setup in the beginning. So don't be too surprised about this. But for us, it's important that we have kind of linear scaling up to this point at least. Now a bit more kind of negative picture is this one for LUMI. So AMD-based system. I don't want to trash AMD at all. So this is just a kind of preliminary result here. So don't take it too much as the final output here. But there's some more challenges that we see here. So it's not. So this would be the linear scaling. We are definitely below. But there's 2 things here. So first of all, we changed our setup so that we went to synthetic data just to avoid this problem of padding or all kinds of other properties that might influence our result. So this is on more realistic kind of data that goes up. So in that sense, also the curve for NVIDIA would be below the base. But then there's also a thing that really software needs to be adjusted to reduce the kind of communication overhead. And there's a crucial plugin that needs to be activated. Without that, it gets really some kind of very big drop, which we don't want to have. Once this plugin is already activated, then we get some better types of scaling that we hope will also continue. So we will test, of course, more. Okay, 5 minutes. Yeah. So now coming to the part that we are doing now. So this is the plan that we are trying to look at. So we want to, of course, use this framework now to make this really big kind of training possible. So we want to take all the data that we have. So maybe skip over some kind of more detailed description of the opus corpus, but there's a lot of parallel data that we have that we also collect more. Then we do now some hyperparameter optimization to find good kind of training parameters, and also do a bit of architecture search to find the best architectures to go further with. Once we have done this, we want to really pipe everything into some big large-scale training for different selected architectures. And then, of course, the extensive analysis and evaluation will come. And after that, we plan to release everything so that people can reuse and take advantage of the models that we have created. So I skipped this one, but just to say, it is actually quite big. So we have terabytes of data, many languages, many sentences that have been aligned. Yeah, okay. So we have some baseline architectures which have been proposed before. So this kind of modularization is not, the only ones doing this. There was this Escolano who did the completely independent components. But maybe quickly going through this one here, which has been proposed by Apple Research, where we also have some kind of modularization. But the interesting thing is that we have language-specific models at the encoder side, and not actually at the decoder side for the target language, which is maybe a bit surprising. And quickly go to that, why that is actually the case. So if we look at this kind of encoder-decoder setup that we have, so we have encoder blocks that read input language to do some kind of representation, and that representation is then piped through the decoder blocks. Then in the decoder, we have a feedback loop that something that is produced here will go as the input into the decoder in the first layer of the decoder. So first, intuitively, you would also think that you can have this kind of one more shared, more target-specific language blocks in the decoder side, but that's because you pipe in target language input in the first block. This doesn't make a lot of sense, and that's why this kind of feedback loop here avoids this kind of hierarchical structuring that you can do on the decoder side. So instead, you can outsource this to the encoder, and so say that the encoder can already prepare the representations for the target language. So it learns to produce something that is easier to generate into the proper target language, so that you don't get on the top level here some kind of universal independent language agnostic representation, but rather something that is already focused on the target language to support the decoder block producing that kind of target language. So that's what we will test. So we will test all those kind of settings. So I'm running a bit faster to this as I have to finish up. So we will do this kind of partially shared encoders. We will test those kind of architecture sharing, the different ways of grouping languages. So for example, by phylogenetic properties or typological properties, or some kind of embedding-based clusters. Then we do this kind of neural architecture search to some extent, and then see also how that works if you can even add new languages incrementally. I feel like I'm really rushing through this, but I have to finish up. So the parameter tuning is actually not that interesting, so it's just about the learning parameters and everything that we want to optimize. So that's what we run starting today. So I just, before coming here, I said that now we will start that. And after that, we will train a so-called flagship model basically on all the data that we have for those selected kind of architectures that we found from the preliminary experiments. So, and then the final point would be distribution and packaging. And hopefully many people will be interested in using that. So that's it. So we have one more kind of thing to just advertise. We have a workshop at EASL next year in March. The deadline is open until the 18th of December. So if anything is interesting here, you're interested in modularity, especially in connection with multilingual NLP, you're free to submit to our wonderful moving workshop. Yeah, it can be any kind of modular, multilingual NLP related things or any modularity. And that's basically it. And I'd like to thank the people who actually do the development and running now certain kinds of experiments. So it's a very male-dominated field, as you can see. So those people are implementing and testing. We also have good support from NVIDIA here. So this is some Nikki Lockby from the NVIDIA IT Center, and otherwise from our team. So that's it. Thank you very much.
Thank you. Perfect timing. We are actually running out of time, but if we have some questions, I think if you have time for a quick one.
Yeah.
So in one of the early plots, you showed how training with different number of languages or sharing differed, and when you had 36 languages, it seemed like sharing everything was the best. And any intuition of why having more languages makes sharing more useful?
Not really. So I think that in that case, you probably have more related languages also in the mixture. So that would be one explanation why you have more benefits from actually sharing a lot. So that might be one explanation. So at least with very few languages, you could see that was a big drop. And that's probably because we had the setup that we had very diverse languages. And then you could imagine that, okay, very much independent components are actually better because they don't interfere each other very much. Whereas if you have a larger pool, then you probably get more this effect of, okay, sharing everything is quite good here. So that would be my explanation. Yeah, I don't have really good, I mean, the figures are a bit kind of varying anyway, but so that would at least be one explanation. We can have, like this, I kind of, so this is the language selection that we had. So 3 languages, Arabic, French, Chinese, so quite different languages, right? Then the 6, we added German, Dutch, and Russian. And then you can see with 9 languages, those were added, and then 12. So you can see that you probably have more patterns of related languages, and that might push this kind of sharing to be more beneficial. And then, of course, the networks itself, the size of the model does not increase. It's always the same parameters. Yeah, but I guess that's mine.
It's a very related question. So this kind of sharing idea also affected with those imbalanced data set. For example, English, it has a very good, very large data set with very high accuracy. But if you refer to any smaller languages, maybe, for example, just like very small language in Africa, definitely you cannot get such a good data set as English and not that big. So it is very imbalanced. So how could you deal with those imbalanced classification or translation? So any detailed techniques?
No, I mean, this also comes down to scheduling, how to train the schedules of training batches. So that relates to that you kind of more balance the data, but you can't do it if you don't have a lot of data for some components. What we want to try is, for example, for very low resource languages, that you have smaller language-dependent components that can be plugged on top of, let's say, a language group component, so that you have good transfer learning across some kind of language groups that are close by languages to that low resource language, for example. And then you could have a nice plugin that specializes this for the small language, if you see what I mean. So that you kind of divide the parameters in a way that are most beneficial for this division of information that you give to the system. Does that make sense? So that you optimize parameter sharing for languages where you need more transfer learning. So building, for example, components that would make it possible to share across those related languages. Yeah, so that's, I think, our take here. So whether all of this works is a bit of an open empirical question anyway. So we probably have more answers once we have some systems here. And I really hope that we can get, so we want to run this over 400 languages. That's our plan. And then I think after that, I can probably answer more properly what our findings are. But you're definitely correct. I mean, if there's very little support for certain languages, then it will just drown in the ocean of other information. And then you might want to have, and that's, I really hope that those specialized components can push it up somewhat so that you really give more focus on those languages.
Makes sense. So another question, can you just predict whether can we use all these techniques, all this work to a foundation model for those multilingual idea? Because I think the idea is pretty good, but it looks that there are a lot of manual works that you need to handle. So I don't know whether it's possible if you want to make it bigger, just like the foundation model, which can be used to do several different downstream tasks.
Yeah. So those bigger models now, I think many have shown that these encoder-decoder models are not that easy to scale up on the same level as those decoder-only models. So also just let's say a BERT like encoder model can also not be scaled up for some reason in the same way, which makes it probably difficult to compare to those gigantic models. As decoder-only models, I would say it's not so easy to modularize because they have this loop that as I showed, the output goes as the input for the next generated. So what I hope is that in a sense, we are scaling up quite a bit as we have all those parameters for different languages. So if you count them all together, it becomes also quite a big model, but we distribute it more into different components. They probably were not on the GPT-4 level of trillions of parameters. Yeah, but what we can definitely do is whatever. So there's also T5 models that are trained for language modeling. So we can also use the same kind of architecture without having translation tasks as the objectives. So we actually do use denoising audio encoders also as one of the tasks here. We had in the attention bridge model also we had the idea that we can combine this with other tasks like audio speech recognition. So that could also be another task. We can even have multitask setups in the same kind of architecture. So I hope that with this flagship model that we try to train, that this also becomes a more generic, I don't have to, but I hope that this is not only for machine translation, but also that we can analyze those different components that can be used for many downstream tasks. And personally, I'm interested in also to see, okay, what does the representation for a language group look like? Does that differ from the universal kind of representation that we have across all languages? In what way does that represent something different? So that point is also interesting.
Yeah, very interesting. Unfortunately, I think we really need to wrap up. So let's
Yeah.
thank the speaker again.
Thank you.